Okay, so now we have a second presentation by Galina, Deeva, and the paper is Predicting Student Success in a Blended Learning Environment.
Hello everyone, I'm happy to present here our research on predicting student success in a blended learning environment. I'm here on behalf of Steven van Ruytenhoven, who was originally going to present it. So I will do my best now to present instead of him. This was a research conducted at KU Leuven, Belgium, that we did together with Daria Bogdanova, me, my name is Galina, Deeva, Steppe van den Broeke, Jochen de Wert, and Monique Snoek. Here is a short overview of the presentation that I'm going to give today. So I will talk a bit about the context and why it's challenging in this to make predictive models in this. I will talk about the data we used, the predictive methodology, and the results we obtained. So what we do, we try to predict the student performance in a blended learning environment. A blended learning environment, as you are of course all familiar with, it's a mixture between online and face-to-face teaching. So now in this research we are dealing not with the data from a MOOC, but from a SPOC, from a small private online course. So of course we have much less data. We don't have thousands of participants, not even 100 participants, but only less than 100. Blended learning is very beneficial for the education of students because it has benefits from both face-to-face and online settings. So, for example, in terms of face-to-face, it allows for better collaboration and communication of students. And in terms of online education, it allows to study anywhere at any time, and therefore it's also very cost efficient. What it also allows us to have is the access to the data of the students studying behavior. But the problem here is that not all of the student learning process is accessible to us. So a lot of data is not being logged because it's not purely online. And what we are doing, we are trying to predict the student performance. It is a very common task in learning analytics to try to predict either students who fail the course or students who will drop out from the course. It is beneficial because we can help those students as early as possible in the course. But
Galina, can I ask you just to speak closer to the mic, please? Sorry, just it gets a bit, yeah.
Okay, I will try. Is it? Well, let me know if it's better. So the challenge here is that we have low sample size, and as I said, only a part of the data is online. There are some studies who do similar research, but mostly they focus on MOOC settings. So that's the main difference. And some of the studies still do some analysis in the blended learning environment. For example, luckily the previous presenter actually talked about the clustering of students based on questions. But yeah, the problem is that we don't have the access to all the data. So the predictive models in this context are somewhat limited. A little bit more about the course that we are dealing with. So we are analyzing data from a mandatory master level course, Architecture and Modeling of Management Information Systems. It is quite a challenging course, and a lot of students have difficulties to complete it. So we have a lot of students who fail the course. The course has live lectures, 8 exercise sessions, a group assignment, and final written exam, and supporting online course. So as you can see, a lot of learning processes going on outside of the course. So one of the research questions that we ask in this study is whether the data that we observe in the SPOC, in the small private online course, is enough to actually have more or less accurate predictions of the student performance. A little bit more about the course. It is hosted on the edX platform, so it's similar to all the edX online courses on edX MOOCs. We didn't use any social tools, so we are not looking into forum data or social network analysis. We are only using the data from the quizzes for example, the data of students watching videos and participating in different kind of quizzes. So we have multiple choice questions, open questions, and other kind of questions for the students. It was held 2 academic years ago in 2018. If you worked with edX data, you know that it comes in a very not immediately user-friendly format. It is in a very nested JSON format. So we extracted the data and then nested it, and of course also anonymized the students. So we used the following attributes of the data. So the data is a so-called log file. So it features the activities made by students with a corresponding time in which this activity or event took place. We have the actual name of the event, so with the time, the session ID, the hyperlinked, which indicates in which part of the course the event took place, the event type. There are in general around 25 different event types in this specific course, and also we have an anonymized user identifier. Then we further preprocess the data using Python. We extracted the chapter and section information from the data, and we also labeled it according to whether a student passed or failed the course. In Belgium, the students are graded out of 20, and below 20 is fail, so this is how we label our students. Then, even though we had already less than 100 students, we still we removed the outliers, because this is important if we want to have robust models. So we used some box plot analysis, so visualized data, and also isolation forest. Both techniques show the same identifiers, so they agreed in outliers, and we removed them from the data. Then the important thing about such data is that it, of course, cannot be immediately used in a predictive model. So we need to create a feature matrix in which each student would have a number of features which we would then feed into a predictive model. So how we featurized the data was we counted the activities that each student did every week for every event type. So we have 25 event types, and we counted the number of events that the student did weekly. And then we aggregated them or averaged them based on 3 kind of time periods. So we had the least granular level with 5 time periods. They're shown on the slide in the table. They are on average 3 to 4 weeks long, and they correspond to a certain meaningful part of the course. And we also had less aggregated data counted bi-weekly and weekly. So we had 9 and 18 weekly periods. What we are looking for in predictive models in this context is good explainability, because we need to know what is going on in the data. We don't want our model to be a complete black box. And we also need the models to be robust against overfitting due to the low sample size, because the problem here is that we have a large amount of features and a low number of cases of students in this context. But I will talk about this later on. So we looked into the performance of 2 models, logistic regression and random forest classifier. logistic regression because it actually has good explainability. It's a simple model, so it's less prone to overfitting. In case of random forest classifier, it shows good performance, maybe a bit more prone to overfitting. We used scikit-learn module in Python to build our predictive models, and we optimized hopper parameters with a grid search inside a cross-validation. These are on the slide are the final parameters of logistic regression that showed the best performance. So we used the L2 regularization with the 0.21 regularization strength and the optimization algorithm, which is shown on the slide. And the models were evaluated using leave one out cross validated accuracy because, as I already mentioned, we have a low sample size. More specifically, we have 61 students after we remove the outliers. So every time we build a model based on 60 students, and then we predict the performance of the one which was left out. And then we average this performance over all the 61 ones. We also looked in the different performance metrics such as precision, recall, F-score, but we are not that sure how much we can trust these scores given the low sample size and the leave one out approach. And so the problem here is a high dimensionality. High dimensionality is something which occurs when we have much more features than we have cases in the model. So, for example, since we have 25 event types, here we have this number. So 125 is the number of features that we get for 5 times period. So if we multiply 5 times 25, we get 125. And for 18 times period, we already have 450 features, which is much more than 61 student that we have. Therefore, we used some, it's very vital here to use some feature selection approach. So we used manual backwards feature selection, and we ended up with only 4 important events that we included in the models, which are submit problem, show answer to a problem, click navigation bar, and play video. We also used some expert-driven knowledge because we have an advantage of being directly involved in the course. So the teachers who taught the course have recommended to use certain events, and we also saw that this corresponds with this intuition corresponds with the performance of the models. So, for example, submit problem. All of these 4 events are very intuitive because, for instance, submit problem indicates how many times did a student submit a quiz, and better performance students might tend to submit more quizzes to train more for the course. Also, show answer to a problem might be negatively correlated with the performance because better students might immediately solve a problem correctly, while worse performance students might need to be shown the answer more often. Click navigation bar is an indication of how much did the student actually use the course, how much did the student navigate around the course. And finally, play video also quite intuitively corresponds to the number of videos watched by the student. So in the end, also about the feature importance, we want to mention, so in the end we used random forest mostly for feature selection process, while logistic regression showed better predictive performance, but I will talk about it a bit later. And also a bit of visual descriptive statistics of what kind of score distribution we were dealing with. We can see that the distribution of grades is pretty close to normal. We have 23 students who failed and 38 students who passed. This Of course, this is not an equal distribution, but it is pretty balanced in a sense that we didn't use any additional data balancing techniques such as oversampling, for example, because it's still pretty close to each other. And also another illustration of how the weights were distributed. And finally, the results. So the best performance has been shown by logistic regression with 5 periods. So while it might be beneficial to use more granular data, we can see that actually probably because of the overfitting problem, the more features we use, the worse is our performance. Logistic regression shows quite consistent results of 80+%, 84% in this context, while random forest classification shows a bit worse results, also not that consistent. So we think that the problem of overfitting might be occurring here. And also it's interesting to see how much data is actually needed to build accurate models. So we look into the data per time period, or for example, data up to first time period, up to the second time period, and so on. And we can see that already in the middle of the course, we can achieve quite good predictive results. And actually, even already in the beginning of the course, they are not that bad. We already have 60%, and then in the middle of the course, we already achieve the maximum predictive accuracy. So the limitations of the study, just to repeat and to outline the limitations, or maybe the challenges of the study of the blended learning context, is the small data sample size, the high dimensionality, and the fact that we don't have enough data to have a separate validation set because we are using the leave one out accuracy. But nevertheless, despite that, we still have quite a high predictive value of 84%, and we can see that already in the middle of the course we achieve good results. So even though a big part of the course wasn't visible for our predictive models, nevertheless, still we can achieve good results, which we are planning to use to identify these cases as early as possible in the course, and then help the students later on. So yeah, the problem of blended learning is that we have a lot of missing data, but now it's not a problem anymore, actually, because now we are all going online for this semester, so we will have a lot of data without any missing values. We are currently working on the future research. It's actually ongoing research in our group. We are looking into detailed time series analysis. So before, we've been using quite a simple way of featurizing the data. We are counting the events, but we are developing a more sophisticated approach using dynamic time warping. It's a technique used in, for example, speech recognition, where the time series going with different speed and in different times are being compared, and if the same pattern occurs in different weeks, we can still find this similarity in student behavior. Also, we are looking into the consistency of students' course interaction, because I think it's important to see not only how many events did the student do, but also how consistent were these events through the time, because the student can do a lot just before the deadline, or work on the course throughout the time, and of course the performance would be affected by that. Also, what we did, we validated the models using different years. So, for example, we used the model built on 1 year and tried to predict the performance on the next year. the problem here is that we need a strong assumption. We have a strong assumption that the course didn't change much, and this is not always the case because we are trying to improve the online course, and this poses some limitations, and predicting performance is not always the greatest, but we are working on that.